The night sky is a beautiful lie. Those scattered stars and galaxies are not isolated islands. They are all connected by an invisible architecture, a skeleton we cannot see. This is the cosmic web, the universe's grand design. It is a vast network of dark matter and gas filaments, a cosmic nervous system linking everything that exists. By the end of this journey, you will understand the 25 fundamental secrets that explain how our universe is built and how it will end. We will uncover why most of the universe's matter has been hiding in plain sight, and how the ghostly imprint of the first moment of creation dictates where galaxies are born. What single idea about the cosmos makes you question everything you thought you knew? This beautiful lie conceals a profound truth, the first secret that reshapes our cosmic reality. The universe has an invisible skeleton. What we see, the brilliant galaxies and shining stars, are merely decorations hung upon a hidden framework. This framework, the cosmic web, is woven from a substance that does not reflect, emit, or absorb light. We call it dark matter. It is the ghost in the cosmic machine, a form of matter that interacts with the universe only through gravity. Think of it like this. If the universe were a grand cathedral, the glittering galaxies would be the stained glass windows and ornate carvings. But dark matter is the flying buttresses and stone arches, the unseen structure that holds the entire magnificent edifice together. Without it, everything would fly apart. This dark matter did not just sit there after the Big Bang. It began to clump together under the relentless pull of its own gravity. Tiny irregularities, quantum whispers from the universe's first instant, acted as seeds. Gravity amplified these whispers, drawing the dark matter into vast sheets and long, thread-like rivers. These were the first filaments of the cosmic web, a skeleton forming in the dark. For decades, this was just a theoretical prediction, a beautiful idea born from mathematics. How could we possibly see a structure made of something invisible? The answer came not from telescopes, but from supercomputers. Pioneering scientists realized that if they could simulate the gravitational dance of trillions of particles of dark matter, they could watch this cosmic skeleton assemble itself. The most famous of these efforts was the Millennium simulation. Run in 2005, it used the combined power of many computers to recreate the growth of the cosmic web across nearly the entire history of the universe. When the results flashed onto screens, they revealed a breathtaking cosmic tapestry, a delicate, interconnected lattice of filaments stretched across billions of light years, with dense clusters of dark matter at the intersections where the threads met. The simulation showed a universe that was not random, but organized on the grandest possible scale. It was a digital prophecy, a map of the invisible world that astronomers would later spend years trying to confirm with real observations. This simulation proved that the luminous galaxies we cherish were destined to form along these dark threads, drawn like pearls onto a string by the irresistible gravity of the unseen. So the first great secret is this: the universe we see is only the glittering surface. Its true shape, its bones and sinews, are made of a shadow substance we are only beginning to understand. But a skeleton alone does not make a living universe. For billions of years after the Big Bang, the cosmos remained in a state of profound darkness. This was the cosmic dark ages, a time when the universe was a featureless, opaque sea of neutral hydrogen gas, with no stars or galaxies to pierce the gloom. The cosmic web existed, but it was a ghostly framework in an utterly black void. The second secret reveals how this darkness was finally broken, and it all began within the densest knots of that invisible web. Gravity continued its patient work, pulling not just dark matter, but also the ordinary hydrogen gas into the intersections of the filaments. These knots became the nurseries for the very first structures in the universe. Within them, gas collapsed, heated, and fused, and the first stars were born. They were not like the stars we see today. These first stars, often called population 3 stars, were behemoths, hundreds of times more massive than our Sun. They lived fast and died young, burning with a ferocious blue-white intensity. Their birth was the cosmic dawn, the moment the universe flickered to life. But the light from these first stars did not simply flood out into empty space. It had to fight its way through the thick fog of hydrogen that filled the cosmos. This is where the architecture of the cosmic web became essential. Think of those first brilliant stars as lanterns lit in a dense, ancient forest. The light does not illuminate the entire forest at once. Instead, it first travels along the paths, the clearings between the trees. In the universe, the filaments of the cosmic web acted as those first pathways. The intense ultraviolet radiation from the massive stars began to eat away at the hydrogen fog, stripping electrons from atoms in a process called ionization. This ionization did not happen evenly in all directions. It progressed fastest along the pre-existing filaments of the web, where the gas was slightly denser and the gravitational pull had already created channels. Over hundreds of millions of years, bubbles of clear, ionized gas grew around the first galaxies, expanding and merging along these cosmic highways. Gradually, the entire fog was burned away and the universe became transparent to light. We are now witnessing the aftermath of this epic dawn. Telescopes like the James Webb Space Telescope are our time machines, peering back to see the very first galaxies being assembled. What they reveal is astonishing. These infant galaxies are not scattered randomly. They are lined up along faint, thread-like structures, exactly where the simulations predicted the filaments of the cosmic web would be. We are seeing the universe's skeleton being decorated with its first points of light. So the second secret is this: the cosmic web was not just a passive scaffold. It was the conductive grid for the universe's greatest awakening, guiding the first light out of darkness and shaping the very architecture of the visible cosmos. Those first galaxies did not grow in isolation. They were connected to a vast, nurturing network, a system of supply lines on a scale almost impossible to comprehend. This is the third secret. The filaments of the cosmic web are not just static architecture. They are dynamic cosmic highways, pulsing with rivers of cold gas that flow for hundreds of millions of light years. This gas is the lifeblood of the universe, the raw fuel for building new stars and feeding hungry galaxies. Without these flowing rivers, the brilliant cities of stars we see today would have starved to death eons ago. The process is both elegant and relentless. The immense voids between the filaments are not completely empty, but they are deserts containing only the most diffuse, thin gas. The filaments themselves, however, are denser. Gravity acts like a cosmic slope, constantly pulling this sparse gas from the voids down into the filamentary channels. Once inside, the gas streams along these threads, picking up speed and density as it flows toward the intersections, the dense knots where galaxy clusters reside. It is a gravitational watershed where the entire landscape of the cosmos funnels material toward the massive hubs. For decades, this was a critical but unproven piece of the theory. We could see the galaxies lined up along the web's predicted structure, but could we see the gas itself flowing? The answer came in 2021, in a monumental breakthrough that felt like turning on a streetlight along a dark, intergalactic freeway. A team of astronomers pointed the European Southern Observatory's very large telescope at a system containing a brilliant quasar, the active, luminous heart of a supermassive black hole in a distant galaxy. This quasar acted like a cosmic flashlight. Its intense beam shone through the universe, and along its path, it illuminated a single, faint filament of the cosmic web. For the first time, they did not just infer the web's existence. They directly observed the glow of cold hydrogen gas streaming along that filament, flowing directly into the quasar's host galaxy. It was a river of creation caught in the act, a direct observation of the cosmic web fueling a galaxy. This was not a simulation. This was a real, glowing thread in the tapestry of the universe, confirming that these filaments are the active supply routes they were theorized to be. The implications are staggering. It means a galaxy's growth and star-forming potential are dictated by its address within the web. A galaxy sitting at a busy intersection where multiple filaments converge receives a constant, rich influx of gas, allowing it to grow massive and form stars for billions of years. A galaxy stranded on a lonely spur might only receive a trickle, causing its star formation to sputter and fade. Our own Milky Way likely owes its spiral richness to the steady flow along specific filaments in our local cosmic neighborhood. So the web is alive with motion, a billion light-year circulatory system where the emptiness of the voids feeds the brilliance of the clusters. This discovery confirms a universe in a state of perpetual flow, where the largest structures are also the grandest conduits, guiding the very material of creation to where it is needed most. This cosmic circulatory system creates a landscape of staggering extremes, the fourth secret of the cosmic web. If the filaments are the rivers, then the walls are the continents and the voids are the oceanic abysses. These are the largest structures the human mind has ever had to comprehend. They are not anomalies, they are the fundamental pattern of the universe, the direct result of the web's gravitational architecture. Where multiple thick filaments of dark matter and gas intersect and weave together, they create immense, dense sheets of galaxies known as Great Walls. The most famous of these is the Sloan Great Wall, a colossal filamentary supercluster discovered in 2003. It is a gargantuan sheet of galaxies over 1.4 billion light-years long, a structure so vast it challenges our understanding of cosmic scale. To stand within it would be to see a sky crammed with galaxies in every direction, a glittering, endless metropolis of stars. These walls are the dense urban centers of the cosmos, where the web's threads are thickest and most tangled. But for every great wall, there is a corresponding emptiness that defies intuition. These are the cosmic voids. The Boötes void is one of the largest known. Discovered in the 1980s, it is a spherical region of space roughly 330 million light-years across. And within that incomprehensible volume, astronomers have found only a handful of galaxies. Our own Milky Way galaxy, with its hundreds of billions of stars, would be a lonely, isolated island in that profound darkness. If you were placed at the void's center, the night sky would be almost perfectly black, with the nearest major galaxy appearing as nothing more than a faint, ghostly smudge. This is not a coincidence of observation. Voids are the empty spaces in the cosmic sponge, the inevitable gaps left behind as gravity pulled all matter into the web's interconnected threads. The walls and filaments form where there was a slight overdensity in the early universe. The voids are the underdensities that got left behind, expanding and emptying out as the web tightened its grip. But the sheer scale of their emptiness presents a profound mystery. Why are some voids, like Boötes, so utterly devoid of galaxies? Gravity alone would suggest a few stragglers should have been left behind. The leading theory points to a more mysterious force, dark energy. This repulsive energy, which drives the accelerated expansion of the universe, acts like a cosmic pressure. In the dense walls, gravity is strong enough to hold galaxies together against this pressure. But in the vast, underdense voids, dark energy finds its greatest influence. It may be actively pushing any remaining wisps of gas and potential galaxies apart, effectively inflating the voids and keeping them pristine and empty. So the fourth secret reveals a universe of shocking contrast, a cosmic fabric woven from both dazzling density and absolute nothingness. The Great Walls show us where the web is strongest. The terrifying voids show us where its grip has failed, and where another, more mysterious force is writing its own chapter in the story of space. The terrifying emptiness of the cosmic voids is a preview of the universe's ultimate fate, a destiny written by a force that works in direct opposition to the web's gravity. This is the fifth secret, a cosmic tug-of-war that will one day tear the universe apart. For billions of years, gravity has been the master architect, patiently weaving dark matter and galaxies into the magnificent cosmic web. But there is a rival on the stage, a mysterious repulsive force we call dark energy. It is the reason the universe's expansion is not slowing down but speeding up. Think of it as a kind of anti-gravity, a constant pressure embedded in the fabric of space itself. Right now, in the dense knots and filaments where galaxies cluster, gravity is still strong enough to hold its ground. Local groups of galaxies, like our own Milky Way and Andromeda, are still bound together and will eventually merge, but on the largest scales, dark energy is winning the war. It acts like an invisible spring, constantly stretching the very space between the filaments of the cosmic web. Over timescales that dwarf human history, this accelerating expansion will have profound and chilling consequences. The delicate threads of the web will begin to stretch and thin. Galaxies that are currently flowing along these cosmic rivers will find the currents slowing, then stopping entirely. The supply of fresh gas from the voids will be cut off, starving galaxies of the fuel they need to form new stars. One by one, the stars will burn out. But the isolation goes deeper. As space itself expands at an ever-increasing rate, the distances between galaxy clusters will grow so vast that light from one cluster will never reach another. Each massive knot of galaxies, once a vibrant metropolis in the web, will become an isolated island universe floating in an infinite, expanding blackness. The cosmos will grow cold, dark, and profoundly lonely. Scientists call this the era of heat death, where all usable energy is exhausted and the universe reaches a state of uniform, icy stillness. There is an even more extreme possibility known as the Big Rip. If dark energy's strength increases over time, its repulsive force could eventually overcome not just the gravity between galaxies, but the very forces that hold galaxies, stars, planets, and even atoms themselves together. In this scenario, the fabric of spacetime would stretch so violently that every structure, down to the subatomic level, would be torn apart in a final, catastrophic moment. Whether the end is a slow freeze or a sudden rip, the conclusion is the same. The great cosmic architecture, the web that took over 13 billion years to build, will be dismantled by the very space it resides in. The brilliant tapestry of galaxies will fade to black, the filaments will snap, and the universe will return to a formless, silent state. This secret forces us to confront a humbling truth. We are living in the cosmic springtime, a brief, golden age where the web is vibrant and full of light, caught perfectly between the fiery birth of the Big Bang and the long, cold night that awaits. That impending cosmic freeze presents us with a strange accounting problem, a mystery that has troubled astronomers for decades. If we tally up all the normal matter we can see, the stars, galaxies, and glowing gas clouds, we come up shockingly short. Over half of the atoms, the protons and neutrons that should have been created in the Big Bang, are simply missing. This is the great missing baryon problem, a gap in our cosmic inventory so large it suggested our understanding of the universe's basic ingredients was fundamentally flawed. The sixth secret solves this puzzle, and the answer was hiding in the most obvious place of all, the filaments of the cosmic web. The missing atoms are not lost. They are simply too hot and too diffuse for our telescopes to see easily. They exist as a searing plasma, a superheated gas with temperatures ranging from hundreds of thousands to millions of degrees. This vast reservoir of matter is called the warm-hot intergalactic medium, or the WIM. It is the ghostly atmosphere of the web itself, filling the filaments with a thin, ionized fog. Think of the cosmic web as a city's power grid. The galaxies are the bright lights in the buildings, easy to spot from miles away. The WIM is like the electricity flowing through the wires, invisible to the naked eye, but absolutely essential for the entire system to function. Detecting this faint, hot plasma is one of the greatest observational challenges in modern astronomy. It does not glow brightly enough to be seen directly. Instead, scientists must use it as a cosmic filter. They look at brilliant, distant objects called quasars, which are the intensely luminous cores of active galaxies. As the quasar's light travels billions of light years to reach us, it passes through the filaments of the WIM. The hot gas in those filaments absorbs very specific wavelengths of that light, leaving tiny, telltale dips in the quasar's spectrum, like a barcode of emptiness. Finding these absorption lines is like trying to spot the shadow of a single, specific thread from a spider's web cast against the blinding glare of a searchlight. It requires immense precision and patience. For years, the evidence was tentative, a few suggestive lines here and there. But recently, by combining data from multiple space observatories, including X-ray telescopes that can sense the highest energy signatures of this million-degree gas, astronomers have finally begun to map the WIM. They are finding it exactly where the simulations predicted, strung along the filaments between galaxies. This discovery closes the cosmic ledger. The missing half of the universe's normal matter has been found. It is not in some exotic, hidden dimension. It is in the superheated highways connecting everything, a diffuse ocean of atoms that contains more mass than all the stars in the universe combined. This means the web is not just a skeleton of dark matter. Its filaments are also thick with ordinary, albeit incredibly hot, atomic matter, completing the picture of where all the stuff of the Big Bang ultimately ended up. This diffuse ocean of hot matter is only the beginning of the story. Where the cosmic rivers of gas and dark matter finally converge, they create environments of unimaginable violence. These are the dense knots of the cosmic web, the galaxy clusters. Here, gravity is not a gentle architect but a ravenous cosmic force. The seventh secret reveals a brutal truth about these hubs. They are arenas of galactic cannibalism. Within a massive cluster, hundreds or even thousands of galaxies are trapped in a relatively small volume of space, all orbiting a common center of gravity dictated by an immense halo of dark matter. The speeds are terrifying, with galaxies whipping past each other at millions of miles per hour. In this chaotic gravitational dance, close encounters are inevitable. When two galaxies pass too near, they do not simply bounce off like billiard balls. Their immense gravitational fields reach out and violently distort each other. Long, streaming tails of stars are ripped loose, creating brilliant bridges and arcs of stolen light. Often, the smaller galaxy is completely torn apart, its stars scattered into a faint haze that joins the cluster's background glow. This is tidal disruption, gravity's method of shredding a galaxy alive, but the ultimate fate for many is a full merger. If the galaxy's paths lose enough energy, they will spiral together over hundreds of millions of years, their structures dissolving into a chaotic, brilliant mess before coalescing into a single, new and larger galaxy. The most massive galaxies in the universe, known as CD galaxies, are the products of this endless feast. They sit like monstrous spiders at the very heart of the richest clusters. A CD galaxy is not a graceful spiral like our Milky Way. It is a featureless, bloated giant, an elliptical behemoth that can contain over 10 times the mass of our own galaxy. It did not grow this large by forming stars peacefully. It grew by devouring its neighbors over billions of years. As smaller galaxies strayed too close to the cluster's center, the dominant CD galaxy's immense gravity captured them. One by one, they were consumed, their stars added to a growing, spherical swarm. This process is so efficient that these central galaxies often have multiple nuclei, the still dense cores of their latest meals orbiting inside them like undigested prey. The entire violent ecosystem is fueled by the dark matter halo, an invisible gravitational pit that holds the cluster together. This halo, containing far more mass than all the visible galaxies combined, dictates the rules of the game. It sets the speeds, it guides the orbits, and it ensures that over cosmic time, everything slowly sinks toward the center, feeding the giant that waits there. So the brilliant cities of the cosmic web are not peaceful metropolises. They are gravitational gladiatorial pits where the largest structures grow by consuming the smaller, in a relentless, slow-motion feast that has been ongoing since the universe was young. Gravity is not the only force sculpting these cosmic rivers. Woven through the searing plasma of the warm, hot intergalactic medium is another, more subtle power, a ghostly grid of magnetism. The eighth secret reveals that the cosmic web is threaded with immense magnetic fields, stretching for millions of light years along its filaments. These are not the simple magnets on your refrigerator. They are primordial forces, perhaps born in the violent turbulence of the universe's first second, and they have been stretched and amplified by the cosmic expansion ever since. As the web's structure formed, these magnetic fields were pulled along with the flowing gas, like invisible threads caught in a river's current. They became aligned with the filaments, creating a vast intergalactic magnetic tapestry. This magnetic web influences everything that moves through it, especially charged particles. When a galaxy forms, drawing in gas from a filament, it must also contend with this magnetic field. The field can exert pressure, slowing the collapse of gas clouds and potentially delaying or even preventing the birth of new stars. It acts as a cosmic regulator, a subtle hand that can either nurture or stifle a galaxy's growth depending on its strength and orientation. These fields also serve as the universe's ultimate particle accelerators. When shock waves from colliding galaxy clusters or exploding stars rip through the filaments, they can send charged particles surfing along these magnetic highways. Protons and electrons are whipped to nearly the speed of light, becoming cosmic rays. The magnetic fields then confine these ultra-high-energy particles, guiding them along the filaments for eons before they might eventually escape into the voids. This means a cosmic ray detected hitting our atmosphere could have begun its journey in a distant cluster, funneled across the universe by the magnetic skeleton of the web. Discovering these fields is a monumental challenge as they do not emit light we can see. Astronomers must look for their fingerprint on the light that passes through. When light from a distant quasar travels through a magnetized filament, its polarization, the direction its waves vibrate, can be subtly twisted. It is like looking at a distant streetlight through a faint cosmic fog that slightly shifts the glare. By meticulously measuring this shift across the sky, scientists are beginning to map the magnetic architecture of the unseen web, confirming that the universe's largest structures are also laced with invisible lines of force. So the web is more than dark matter and hot gas. It is a magnetized ecosystem where primordial magnetism guides, constrains, and accelerates the very particles that make up the visible cosmos, adding a layer of profound and beautiful complexity to the dark architecture of space. That magnetic tapestry is a relatively recent discovery, but the web's influence leaves an imprint from the very dawn of time. To understand the ninth secret, we must look at the oldest light in the universe, a fossil glow that bathes all of space. This is the cosmic microwave background, the faint afterglow of the Big Bang itself. Released when the universe was just 380,000 years old, this light has been traveling for over 13 billion years to reach us. It is a nearly perfect snapshot of the infant cosmos, a map of tiny temperature variations that were the seeds for all future structure. But as this ancient light makes its final journey to our telescopes, it must pass through the fully grown cosmic web, and that journey changes it. The immense gravitational pull of the web's massive filaments and galaxy clusters acts like a lens on the fabric of space. As the CMB photons fly through these regions, they must climb out of the deep gravitational wells created by dark matter. In a universe dominated by matter, the energy lost climbing out would be perfectly regained later. But our universe is not dominated by matter alone. Dark energy, that mysterious force accelerating cosmic expansion, changes the rules. When a CMB photon enters a massive cluster's gravitational well, the well itself is subtly weakening over cosmic time due to dark energy's influence. So when the photon climbs out, it finds the well is shallower than when it entered. It escapes with a little extra energy, appearing slightly hotter or colder in a very specific pattern. This phenomenon is called the integrated Sachs-Wolf effect. It is an incredibly subtle distortion, a whisper of a temperature shift imprinted on the ancient light. But for scientists, it is a direct signal, a shadow cast by the unseen web onto the most important photograph in cosmology. By meticulously scanning the cosmic microwave background with satellites like Planck and WMAP, astronomers can search for these telltale hot and cold spots that align with the positions of known galaxy clusters and filaments. It is like holding a fossil up to the light and seeing the shadow of a modern tree superimposed upon it. The tree, the cosmic web, was not there when the fossil formed, but its shadow proves its existence and reveals its shape. This technique allows us to map the distribution of dark matter across vast swaths of the universe, not by seeing the dark matter itself, but by seeing how its gravity has warped the oldest light we can observe. It confirms that the grand architecture we see in galaxy surveys today grew directly from those tiny seeds in the CMB, and that the invisible hand of dark energy is already leaving its mark on the relationship between the ancient past and the present structure. So the ninth secret ties the beginning to the now, using the universe's first light as a backlight to illuminate the dark skeleton that shapes everything we see. That ancient light holds a memory of the first moment, a whisper from a time before time. To uncover the 10th secret, we must travel back further than the cosmic microwave background to a period so brief it defies comprehension. In the universe's very first fraction of a second, a phenomenon called inflation occurred. Space itself expanded faster than the speed of light, inflating a subatomic speck of reality into a cosmos of macroscopic size. During this unimaginable growth spurt, the empty vacuum of spacetime was not perfectly smooth. According to quantum mechanics, empty space is a seething foam of virtual particles, constantly flickering in and out of existence. These are quantum fluctuations, tiny ripples of energy that appear and vanish in an instant. In the normal world, they are invisible and irrelevant, but during inflation, something miraculous happened. As spacetime expanded exponentially, these microscopic ripples were stretched along with it. A quantum flicker that was once smaller than a proton was suddenly inflated to a scale of light years, then millions of light years. The random hills and valleys of this quantum foam were frozen into the very fabric of the expanding universe, becoming permanent variations in density. Think of it like baking a loaf of raisin bread. The dough represents the fabric of spacetime. As you knead the dough, you create tiny, random air pockets, the quantum fluctuations. Then you place the dough in the oven to rise. That rise is cosmic inflation. It expands the entire loaf dramatically, and those tiny, random air pockets are stretched into huge, irregular bubbles. When the loaf is finished, the distribution of raisins, which represent matter, is not even. The raisins cluster where the bubbles are and avoid the dense areas in between. In our universe, the stretched quantum ripples became the ultimate blueprint. Slightly denser regions had a tiny bit more gravitational pull. Over the next 13.8 billion years, dark matter and gas were drawn to these spots. The densest ripples became the knots where galaxy clusters would form. The slightly less dense ridges became the filaments, and the underdense regions, the quantum valleys, expanded into the vast cosmic voids we see today. This means the entire architecture of the cosmic web, from the great walls to the terrifying emptiness of the Boötes void, is a direct result of random quantum jitters magnified to a cosmic scale. The pattern of galaxies across the night sky is in essence a quantum fingerprint blown up to the size of the observable universe. Your existence, the Earth, the Sun, and the Milky Way all ultimately trace back to a random fluctuation in a field of energy that lasted less than a billionth of a second. It is a humbling and beautiful connection, linking the smallest rules of reality to the largest structures imaginable. Quantum ripples may have set the stage, but to read the story they wrote, astronomers needed a special kind of codebreaker. That tool is the Lyman alpha forest, a cryptic but beautiful pattern hidden within the light of the most brilliant beacons in the universe. To understand it, picture a single, impossibly distant quasar, the active heart of a young galaxy, shining with the power of a trillion suns. Its light is a pure white beam containing every color of the rainbow. But as this light travels for billions of years to reach us, it does not travel through empty space. It cuts a straight line through the cosmic web, piercing countless filaments of gas. And within those filaments lurks neutral hydrogen, the most basic element in the cosmos. This hydrogen has a very specific appetite. It loves to absorb light at one precise ultraviolet wavelength, known as the Lyman alpha line. So every time the quasar's light passes through a cloud of hydrogen in a filament, a tiny bite is taken out of its spectrum at that specific color. Because the universe is expanding, each cloud of hydrogen is being carried away from us at a slightly different speed. This stretches the absorbed wavelength, shifting it toward the red end of the spectrum. The result is breathtaking. Instead of seeing one single absorption line from one cloud, astronomers see thousands. The quasar's smooth spectrum becomes a dense thicket of dark lines, each one a fingerprint from a different filament of gas at a different distance along the line of sight. This is the Lyman alpha forest. It is not a physical forest, but a forest of data, a barcode of emptiness that tells an epic story. By decoding this barcode, scientists can perform a kind of cosmic tomography. Each absorption line reveals the density, temperature, and distance of the hydrogen cloud that created it. By studying the thickness and spacing of the lines, they can map how the gas is distributed. Are the lines sparse and weak? That indicates a thin, diffuse filament. Are they thick and clustered together? That reveals a dense knot, a proto-cluster of galaxies in the making. This allows astronomers to create a one-dimensional core sample of the universe, drilling through time and space along a single, brilliant beam. They can trace how the gas evolved from the smooth, dense distribution of the early universe to the clumpy, web-like structure we see today. The forest thins out as we look back in time, confirming that the web took billions of years to fully form. This ghostly barcode, written in missing light, is our most powerful direct probe of the cosmic web's gaseous skeleton, allowing us to trace its invisible threads across the deepest reaches of time and space. Decoding the Lyman alpha forest is like listening to a single, complex note to understand the entire symphony. To hear the full orchestra, we need a map of the entire cosmic stage. This is the work of cosmic archaeology, and the 12th secret reveals how we are building the most detailed atlas of the universe ever conceived. These are the galaxy surveys, monumental scientific endeavors that do not look at one object but at everything. Instead of focusing a telescope on a single beautiful galaxy, these projects point it at a huge patch of sky and take a census, cataloging the positions, colors, and distances of millions upon millions of galaxies. The most famous of these is the Sloan Digital Sky Survey. For over 2 decades, a dedicated telescope in New Mexico has been systematically scanning the heavens. It does not take pretty pictures for posters. It gathers raw data, measuring the light from countless faint smudges. For each galaxy, a key piece of information is its redshift, the stretching of its light caused by the expansion of the universe. Redshift acts as a cosmic yardstick. The more stretched the light, the farther away the galaxy is, and the longer its light has been traveling to reach us. By combining a galaxy's position on the sky with its redshift distance, astronomers can place it in a 3-dimensional map of the cosmos. The result of the Sloan survey is nothing short of breathtaking. It is a three-dimensional pointillist painting on the scale of the observable universe. When you plot the positions of several million galaxies, a pattern emerges from what first looks like random noise. You do not see the galaxies themselves as much as the empty spaces between them. The galaxies trace out the dense walls and filaments, outlining the voids like glowing sand on a dark beach. The map reveals the cosmic web in all its spongy, filamentary glory, a structure so vast it makes individual galaxies seem like dust motes, but this is just the beginning. The next leap forward is already underway with the Vera C. Rubin Observatory's legacy survey of space and time. This project is on an entirely different scale. Over 10 years, it will image the entire southern sky every few nights, not once, but over and over again. It will not catalog millions of galaxies, it will detect tens of billions. This relentless watch will create a dynamic, living map of the cosmic web, allowing scientists to see how structures change over time and to catch fleeting cosmic events on an unprecedented scale. These maps are far more than just pretty pictures. They are the ultimate testing grounds for our deepest theories of physics. By precisely measuring how galaxies cluster within the web, scientists can weigh the invisible dark matter halos that hold them together. They can measure how the web's growth has slowed or accelerated over cosmic time, putting the repulsive force of dark energy on trial. They can even test the laws of gravity themselves on scales far larger than our solar system to see if Einstein's theory holds true across the entire universe. Every filament, every void, every knot in this grand map is a data point in the greatest experiment ever conducted, an experiment written across the sky itself. Those billions of galaxies mapped by cosmic surveys are not all quiet islands. At the heart of many, a monster lies in wait, growing fat on the bounty delivered by the web itself. The 13th secret connects the largest architecture to the most extreme objects, revealing that supermassive black holes are direct products of the cosmic web's nourishing flows. These gravitational abysses, containing millions or even billions of times the mass of our Sun, do not simply appear, they are fed, and their primary supply lines are the dark matter filaments that channel rivers of cold gas across the cosmos. When a galaxy sits at a busy intersection of the web, it receives a constant, rich influx of this star-forming fuel, but not all of this gas makes it to the stellar nurseries. A significant portion is funneled relentlessly toward the galactic center, swirling down into the waiting black hole like water down a cosmic drain. This process, called accretion, is how a black hole grows. The web's structure directly dictates the menu. A galaxy embedded in a thick, gas-rich filament will have a well-fed central black hole, one that may become active and luminous. A galaxy on a sparse, lonely thread might host a black hole that is starving and dormant, but there is a second, more violent delivery method. The web's gravitational choreography does not just bring gas together. It brings entire galaxies on collision courses. When two galaxies merge, as they often do in the dense knots of the web, their central black holes are dragged toward the new galaxy's core. As they spiral together, their immense gravitational forces stir up and compress the surrounding gas, sending vast new reservoirs tumbling toward the newly formed, even larger black hole. This merger-fueled feast is a spectacle of pure cosmic power. As matter spirals into the black hole at nearly the speed of light, it forms a superheated disk of plasma, glowing with the energy of billions of stars. Fierce magnetic fields coiled within this maelstrom can launch jets of charged particles that blast out across intergalactic space for millions of light years. This is the birth of an active galactic nucleus, and in its most extreme form, a quasar. A quasar is so luminous it can outshine its entire host galaxy, becoming a beacon visible across the observable universe. The very quasars we use as flashlights to probe the web's faint filaments are themselves products of the web's dynamics. They are the brilliant, screaming evidence of black holes feasting at the crossroads of the cosmic rivers, a direct link between the universe's largest scale structure and its most energetic, compact phenomena. So the web does not just build galaxies, it also ignites the furnaces at their hearts, turning the gentle flow of intergalactic gas into the most violent and luminous fires in creation. These brilliant quasars mark the busy intersections of the cosmic map, but if we look away from the bustling hubs, we find a different kind of inhabitant in the web's quieter neighborhoods. Drifting in the outskirts of galaxy clusters or along the faintest tendrils of filaments are ghost ships, galaxies so ethereal they almost aren't there at all. These are the ultra-diffuse galaxies, and they hold the 14th secret, a mystery of cosmic failure and survival. The most famous of these phantoms is Dragonfly 44, discovered in the Coma cluster. By all gravitational accounts, this galaxy has a mass comparable to our own Milky Way, meaning it possesses a huge halo of dark matter, but that is where the similarity ends. Where the Milky Way blazes with hundreds of billions of stars, Dragonfly 44 is a faint, wispy smudge. Its stars are so thinly spread that the galaxy is nearly transparent, a ghostly cobweb against the dark. If you lived on a planet inside it, your night sky would be almost empty, with the nearest star so far away that other galaxies might shine brighter in your heavens. The existence of such objects forces a difficult question. How can a galaxy have the gravitational heft of a giant, yet the visible substance of a dwarf? The leading theories point to two tragic stories, both dictated by the cosmic web. The first is a story of starvation. Perhaps these ultra-diffuse galaxies are primordial, some of the first structures to form in the early universe. They assembled their massive dark matter halos early on, but they had the misfortune of forming in a sparse region of the web, a quiet backwater where the filaments were thin. Without a steady, rich flow of gas from the cosmic rivers, they simply never gathered enough fuel to ignite prolific star formation. They are cosmic stillbirths, massive in potential but frozen in a faint, infant state. The second story is one of robbery. A galaxy might have formed normally with a healthy population of stars, only to later fall into the gravitational domain of a massive cluster. As it plunged through the cluster's dense, hot interior, a process called ram pressure stripping could have occurred. Imagine the galaxy as a dandelion seed head flying through a torrential rainstorm. The superheated plasma that fills the cluster acts like that rain, violently blowing away the galaxy's remaining cool gas, the very fuel needed to make new stars. The existing old stars remain, held together by their dark matter halo, but the galaxy is left sterile and fading, its light stretched thin across a vast volume. These ghostly galaxies are therefore critical evidence. They show us the profound influence of a galaxy's address within the web. Thriving in a dense filament leads to brilliance and growth. Stranded in a sparse zone or ravaged by a cluster's environment leads to a different fate, a haunting, diffuse existence. They are the cosmic equivalent of shadows, reminding us that for every brilliant city in the web, there are countless faint echoes, galaxies that whisper stories of what might have been. These ghostly galaxies are faint signposts in a map that is also a calendar. The 15th secret reveals the cosmic web is a time machine, a living record of cosmic evolution. Because light travels at a finite speed, looking out into space is literally looking back in time. When we observe a galaxy a billion light years away, we see it as it was a billion years ago. This simple fact transforms the three-dimensional maps from galaxy surveys into something extraordinary, a flipbook of the universe's history. By cataloging galaxies at different distances and therefore different redshifts, astronomers can slice the cosmos into epochs. They can compare the web as it was 5 billion years ago to the web as it is today, watching its structure change over cosmic time. The story these slices tell is one of relentless expansion and gradual thinning. In the early universe, the web was a more compact, intricate tapestry. The filaments were thicker and denser, like the tightly woven roots of a young tree. Galaxy clusters were closer together, and the rivers of gas flowing along the filaments were more vigorous, fueling frantic bursts of star formation in the infant galaxies. The universe was a more crowded, more dynamic place, but as eons passed, dark energy's influence grew. The accelerating expansion of space itself began to stretch the grand architecture. The filaments, those cosmic highways, started to pull apart. The distances between galaxy clusters increased. The rivers of gas flowing into them became slower, thinner streams. The web did not disappear, but it grew more diffuse, its threads becoming more tenuous as the voids between them inflated. We see this in the data. When astronomers look at very high redshift, meaning very distant and ancient slices of the universe, they find that galaxies are more strongly clustered along the predicted filaments. The web's pattern is sharper, more pronounced. In our local modern universe, the pattern is still there, but it is more stretched out, the galaxies more spread out along the filaments, with greater gulfs of empty space between the major knots. This provides a direct, observational movie of how gravity and dark energy have shaped the cosmos. It is not a simulation, but a real-time, or rather a deep-time, chronicle written in the positions of billions of galaxies. Each map is a single frame, and by stacking them in order, we watch the universe grow up, we see its skeleton expand, and we witness the slow-motion drift of its great cities away from one another, pulled apart by the invisible force rewriting its future. This cosmic flipbook holds a hidden rhythm, a faint echo from a time when the universe was not silent, but filled with a deafening roar. The 16th secret is written in sound, a sonic fingerprint from the first 380,000 years of creation. In that seething, primordial plasma, ordinary matter was not a passive gas. It was a fluid locked in a ferocious tug of war with light. Photons, the particles of light, were so densely packed that they exerted an immense outward pressure, pushing against the inward pull of gravity. This created oscillations, powerful sound waves that rippled through the hot soup of protons and electrons at over half the speed of light. Think of a stone dropped into a pond, sending out concentric rings. Now imagine that pond is the entire observable universe, and the stone is a random quantum fluctuation from the Big Bang. These were not gentle waves. They were tsunamis of density, compressing matter into spherical shells that expanded outward for hundreds of millions of years. Then the music stopped. When the universe cooled enough for atoms to form, a moment called recombination, the photons suddenly decoupled from the matter and streamed away as the cosmic microwave background. Without the photon pressure to drive them, the sound waves froze in place instantly. The expanding shells of matter were caught mid-ripple, leaving behind a cosmic fossil, spherical ripples of slightly denser material embedded in the fabric of space. This fossil is known as baryon acoustic oscillations. The key is its scale. Because the speed of sound in that early plasma is known, the distance these waves traveled before freezing is a fixed length, a standard ruler imprinted on the cosmos. That ruler is about 500 million light-years long. For billions of years, as the cosmic web formed under gravity, galaxies preferentially formed along these frozen shells. This means that if you take a massive galaxy survey map and measure the statistical distance between pairs of galaxies, you will find a subtle but unmistakable excess of galaxy pairs separated by that specific 500 million light-year scale. It is as if the universe has a preferred spacing, a faint echo of its first sonic boom. For astronomers, this is a gift of unimaginable precision. By measuring this BAO scale in the web at different cosmic epochs, they can track how the ruler itself has been stretched by the expansion of the universe. Measuring it in nearby galaxies tells us the expansion rate today. Measuring it in galaxies billions of light-years away tells us the expansion rate billions of years ago. By comparing these, we can chart the entire history of cosmic expansion with extraordinary accuracy, putting the accelerating effect of dark energy on a graph. This sonic imprint, a vibration from the universe's first fiery moments, has become our most reliable yardstick for measuring the fate of everything. That sonic ruler gives us the scale of the web, but it does not tell us how the galaxies within it are oriented. There is a subtle, almost eerie connection between a galaxy's personal spin and the immense architecture that birthed it. The 17th secret suggests that galaxies might not tumble through space randomly. Their axes of rotation, the imaginary lines around which they spin, could be aligned with the very filaments of the cosmic web they call home. This idea stems from a process called tidal torque, a gravitational effect that works on a truly cosmic scale. As a proto-galaxy, a vast cloud of gas and dark matter, begins to collapse under its own gravity, it does not exist in isolation. It sits within the gravitational landscape of the surrounding cosmic web. The web's filaments and sheets exert a gentle but persistent shear force, a stretching pull from different directions. Think of it like placing a ball of dough on a table and pulling the tablecloth in one direction. The dough will not just compress, it will also start to twist. In the early universe, the collapsing gas cloud experienced this gravitational shear from the large-scale structure around it. This tidal force imparted a tiny amount of angular momentum, a slow spin, to the cloud as it fell inward. That initial twist, imprinted billions of years ago, could have set the rotational axis for the majestic spiral galaxy that eventually formed. If this theory is correct, then galaxies within the same filament might show a preferred orientation, their disks spinning like coins rolling along the same cosmic groove. Proving this is a monumental statistical challenge. It requires measuring the precise tilt of millions of galaxies and comparing those angles to the mapped direction of the filaments they inhabit. Early results from massive surveys like Sloan are tantalizing. Studies have found that the spin axes of giant elliptical galaxies, and perhaps the central regions of some spirals, do show a weak but statistically significant alignment with the local web structure. It is as if the ghostly hand of the web's gravity reached out in the first moments of a galaxy's life and gave it a gentle, defining nudge. This connection, if firmly established, would be a profound unification. It would link the personal identity of a galaxy, the direction of its majestic pinwheel dance, to the grandest gravitational patterns in the universe. Your galaxy's spin could be a fossil memory, a whisper of the specific filamentary highway down which its building blocks flowed so long ago. That subtle alignment of a galaxy's spin is a clue to its birth, a whisper of the specific pathways its building blocks traveled. But how did those building blocks, the raw gas for stars, actually reach the infant galaxies in the chaotic early universe? The 18th secret reveals a surprising and elegant delivery system. The first massive galaxies did not form from a slow, gentle rain of gas. They were fed by narrow, icy rivers flowing directly down the dark matter filaments of the young cosmic web. These are the cold streams, and they are the key to unlocking the universe's first brilliant age of star formation. In the modern, mature universe, a galaxy like our Milky Way sits within a massive, hot atmosphere of gas called a halo. This halo is heated to millions of degrees, likely by shock waves from supernova explosions and the energy output of the central black hole. For new gas to reach the galaxy's star-forming disk, it must first plunge into this hot halo. The gas heats up, slows down, and must cool for millions of years before it can finally condense into stars. It is a slow, inefficient process, but the early universe was a different place. The first massive galaxies were assembling during the cosmic dawn, just 1 billion or 2 years after the Big Bang. Their dark matter halos were massive, but they had not yet built up those immense hot atmospheres. The space around them was still relatively cool. This created a perfect opportunity for a more direct route. Theoretical models and sophisticated computer simulations show that the pristine hydrogen and helium gas from the intergalactic medium did not fall onto these galaxies from all directions. Instead, it followed the path of least resistance, flowing along the dense, pre-existing filaments of the dark matter web. Think of the nascent cosmic web as a system of icy mountain aqueducts and the proto-galaxies as thirsty cities in the valleys. The cold streams are the meltwater rivers that flow directly from the glaciers, down the mountain channels, and straight into the city reservoirs. They bypass the warm lowlands entirely. In the cosmic version, these streams are narrow, only a few tens of thousands of light years across, yet they can stretch for millions of light years along a filament. They remain cold because they are dense and shielded, and they travel so quickly that they do not have time to heat up from interaction with any diffuse surrounding gas. When these frigid rivers of gas, traveling at hundreds of kilometers per second, finally slam into the core of a growing galaxy, they deliver a massive, sudden infusion of star-forming fuel. This is not a gentle trickle, it is a fire hose of creation. The gas is already cold and dense, so it can collapse almost immediately into vast, luminous clouds that birth thousands of stars in a single burst. This explains a long-standing puzzle: how the earliest massive galaxies we observe with telescopes like James Webb managed to form so many stars so quickly. They were not slowly gathering material, they were being force-fed by the cosmic web's direct intravenous lines. These cold streams are likely the reason the universe experienced its peak of star formation around 10 billion years ago, a period known as cosmic noon. As the universe aged and galaxy halos grew hotter, these delicate cold delivery systems became more vulnerable. They could be disrupted by shock heating or torn apart by galactic interactions. The rivers slowed to a trickle, and star formation rates in most galaxies began their long, steady decline. So the brilliant dawn of galaxies was not a gentle awakening. It was a sudden, frigid flood, a torrent of creation channeled by the invisible architecture of the web itself. Those frigid rivers of creation do not flow silently. Where they collide, they create shock waves of cosmic violence, turning the web's architecture into something far more dynamic. The 19th Secret proposes a staggering idea. The cosmic web is the universe's largest and most powerful particle accelerator. It does not use magnets in a tunnel, but gravity and supersonic collisions on a billion light-year scale. The process begins with the relentless flow itself. As vast rivers of gas traveling at hundreds of kilometers per second pour into the dense knots of galaxy clusters, they do not merge smoothly. They slam into the cluster's existing hot atmosphere like a waterfall hitting a lake at hypersonic speeds. This creates titanic shock fronts, expanding spheres of energy that ripple through the intergalactic medium. Within these immense shock waves, the chaotic turbulence and tangled magnetic fields that thread the web become a natural engine. Charged particles like protons and electrons get caught in the churning maelstrom. They are reflected back and forth across the shock front, gaining a little more energy with each crossing, like a tennis ball being volleyed with increasing force between two rackets moving toward each other. Over time, this Fermi acceleration process can whip particles to velocities so close to the speed of light that they carry energies far beyond anything we can create in our most powerful machines on Earth. These particles become cosmic rays, the mysterious high-energy radiation that constantly bombards our planet. For over a century, the origin of the most energetic cosmic rays has been one of astrophysics' greatest puzzles. A single particle at the extreme end of the spectrum can carry the kinetic energy of a professionally thrown baseball, all compressed into a single proton. Where in the universe could such an unimaginable cannon exist? The web's most violent intersections are now the prime suspects. The collisions of galaxy clusters themselves, the most energetic events since the Big Bang, are likely the ultimate cosmic ray factories. When two clusters, each containing thousands of galaxies and trillions of stars, plow into one another over billions of years, they release more energy than a million supernovae. The shock waves generated are of almost inconceivable power, creating perfect conditions to accelerate particles to those extreme, unexplained energies. The magnetic fields woven through the filaments then act as containment tubes, guiding these ultra-high-energy particles for millions of years before they might finally escape into the void. This means a cosmic ray detected by an observatory on Earth could be a messenger from a collision that happened in a distant filament a billion years ago, its path a winding journey along the magnetic highways of the web. By tracing the arrival directions of these rare, ultra-high-energy particles and matching them to the positions of massive galaxy clusters or colliding filament structures, scientists hope to finally pinpoint the universe's natural supercolliders, turning the map of the web into a schematic for the most powerful engines in existence. Those unimaginable particle accelerators operate within the rules of our one visible cosmos, but what if our universe is not alone? The 20th secret takes us to the edge of known physics, into a breathtaking and speculative possibility. The grand architecture we call the cosmic web may be a local pattern, one unique tapestry in an infinite gallery of realities. This idea springs from the theory of eternal inflation, an extension of the same inflationary process that stretched our quantum seeds. In this picture, the rapid expansion of spacetime did not stop everywhere at once. It stopped in our local region, allowing a stable universe like ours to bubble into existence. But beyond the horizon of our observable cosmos, inflation may still be happening eternally, giving birth to an endless froth of other bubble universes, each with its own distinct laws of physics. This is the multiverse hypothesis. If this is true, then the specific properties of our universe, the exact strength of gravity, the nature of dark energy, the precise recipe of particles were set when our bubble formed. They are not universal constants but local bylaws, and this has a direct, profound implication for the cosmic web. The entire structure depends on a delicate balance. The exact spectrum of those initial quantum fluctuations, the amount of dark matter versus normal matter, the repulsive strength of dark energy, all of these factors dictated how the web formed. Tweak just one of these fundamental numbers and the cosmic architecture changes completely. In a bubble universe where dark matter is more abundant, gravity might have won too quickly, causing all matter to collapse into a single, monstrous black hole before any delicate filaments could form. In a bubble where dark energy is much stronger, the repulsive force might have acted immediately, blowing everything apart before gravity could pull matter into any structure at all. There could be universes where the web is far more intricate, a dense lacework of filaments with galaxies packed shoulder to shoulder, or universes where the voids are even more terrifyingly dominant, with only a few lonely stars adrift in eternal night. Our particular web, with its balance of great walls and vast voids, its filaments and clusters, might be a rare cosmic outcome, a Goldilocks pattern that allowed for the gradual, rich evolution that led to galaxies, stars, planets, and us. This frames our entire reality in a startling new light. The magnificent structure we are painstakingly mapping, with all its violence and beauty, is not necessarily the way things had to be. It is simply the way things are here in this one bubble. The quantum fingerprint we see blown across the sky is our local signature. Other bubbles may have entirely different fingerprints or perhaps no coherent pattern at all. So when we study the web, we are not just learning about our universe. We might be reading the unique charter of our own cosmic neighborhood, a single, brilliant thread in a multiversal tapestry of infinite variety. Our universe's dark matter may be hiding in the oldest shadows imaginable. This is the 21st secret, a hunt for monsters born in the first chaotic second of time, primordial black holes. These are not the stellar mass black holes formed from collapsing stars, nor the supermassive giants at galactic centers. These would be relics of the Big Bang itself, forged when extreme density fluctuations in the infant cosmos collapsed directly into singularities. They could be as small as an asteroid or as massive as a star, and they have long been a compelling candidate for at least a portion of the mysterious dark matter. If they exist in significant numbers, they would not be scattered randomly. Gravity would have woven them into the same cosmic tapestry as everything else. They would naturally fall into and cluster along the filaments of the cosmic web, tracing its invisible architecture with invisible mass. Finding them, however, is a detective story of supreme subtlety. Scientists are pursuing several ghostly signatures. The first is gravitational lensing. If a primordial black hole passes in front of a distant star, its gravity will warp space-time, acting as a tiny lens. For a brief moment, the star's light will magnify and brighten in a characteristic flash. Astronomers use vast surveys to monitor millions of stars, looking for these telltale, unexplained flickers that could betray a hidden population of black holes drifting through the galactic halo. A second method looks at the cosmic microwave background. If numerous small primordial black holes existed in the early universe, their evaporation or their gravitational effects on the surrounding plasma could have left subtle imprints on that ancient light, minute distortions in its temperature patterns. We are sifting through the universe's first photograph for the shadows of its first monsters. Perhaps the most dramatic potential signature comes from the ripples in space-time itself. Gravitational wave observatories like LIGO and Virgo listen for the cosmic chirps of black holes merging. Some of the collisions they have detected involve black holes of masses that are puzzling if they only come from dead stars. Could these be mergers of primordial black holes that have been dancing around each other for billions of years within a dark matter filament? Each unexplained event, each odd mass black hole, raises the tantalizing possibility that we are hearing the echoes of the web's densest, darkest knots. This hunt connects the largest structures in the universe to the most fundamental questions in particle physics and cosmology. Finding a population of primordial black holes would not just solve the dark matter puzzle, it would open a direct window into the conditions of the universe's first infinitesimal moment, revealing a cosmos where the fabric of reality itself was knotted into dark seeds that would one day guide the birth of galaxies. The hunt for primordial black holes is a search for shadows, but our cosmic neighborhood holds a different kind of ghost, a problem of absence that has haunted astronomers for years. This is the 22nd secret, the case of the missing satellites, our most sophisticated simulations of cosmic structure, which so beautifully predict the grand filaments of the web, also make a very specific prediction about our own galactic backyard. They tell us that the Milky Way's immense dark matter halo should be swarming with thousands of smaller satellite halos, clumps of dark matter that are massive enough to host their own small galaxies. Yet when we look, we find only a few dozen faint dwarf galaxies orbiting us. Where are all the rest? This glaring mismatch is one of the most persistent challenges to our standard model of cosmology. It suggests that something is either wrong with our understanding of dark matter, or that a powerful cosmic process is actively hiding these satellites from our view. The leading solution points directly to the interconnected nature of the cosmic web and the harsh environment of the early universe. In the standard picture, those thousands of small dark matter halos did form. They are likely out there right now, orbiting the Milky Way, but they may be almost completely dark, devoid of the stars that would make them visible to our telescopes. The culprit is a phenomenon called reionization, that same cosmic dawn when the first stars burned away the hydrogen fog. But this awakening had a dark side. The intense ultraviolet radiation flooding out from those first massive galaxies did not travel evenly in all directions. It was channeled and amplified along the very filaments of the young cosmic web, turning these cosmic highways into conduits of sterilizing energy. Imagine a forest fire sweeping through a valley. The flames race fastest along dry riverbeds and game trails, the pre-existing pathways through the terrain. In the infant cosmos, the UV radiation from the first stellar cities raced along the filaments. For any small, vulnerable dark matter halo sitting along or near these brilliant pathways, it was a catastrophe. These halos had relatively weak gravity. When the flood of high-energy photons hit them, it heated their scant reservoirs of hydrogen gas to extreme temperatures. The gas became too energetic to collapse and form stars. In many cases, the radiation might have stripped the gas away entirely, blowing it out into intergalactic space. The result was a cosmic sterilization. These small halos were left as barren, dark matter ghosts, possessing the mass to be galaxies but lacking the stars to light them up. They became the missing satellites invisible to our optical surveys. This elegant solution reconciles the simulations with our observations. The dark matter halos are there just as predicted. But the interconnected, luminous nature of the young cosmic web created an environment too harsh for the smallest structures to ignite. It was a cosmic scale pruning, where the same forces that guided the growth of giants also suppressed the birth of dwarfs. The search now is to find these dark halos through other means, perhaps by detecting the faint gamma-ray glow that might emanate if dark matter particles within them were to annihilate, or by spotting the subtle gravitational distortions they impose on the light of background stars. Each potential discovery would not only solve a famous puzzle, but would further prove how the web's environment dictates the fate of everything within it, from the brightest galaxy to the darkest silent halo. The missing satellite problem hints at forces beyond our current models, leading to a question that strikes at the very foundation of physics. Could the detailed structure of the cosmic web reveal that Einstein's theory of gravity is incomplete? For over a century, general relativity has been our gold standard, explaining everything from the orbit of Mercury to the bending of light around stars. But it depends on a mysterious ingredient, dark matter, to explain the motions of galaxies and the shape of the web. Some scientists wonder if the problem is not with an unseen substance, but with the law of gravity itself. This is the 23rd secret, a cosmic trial being held on the largest courtroom imaginable, where the web's architecture is the key witness. The leading alternative is a theory called modified Newtonian dynamics, or MND. It proposes that gravity does not weaken as quickly over vast distances as Newton and Einstein predicted. Instead, at the extremely low accelerations found between galaxies and within the diffuse filaments of the web, gravity gets a subtle second wind. This tweak to the law could, in theory, explain why galaxies rotate as if they contain more mass than we see, without needing any dark matter at all. But if gravity behaves differently, the cosmic web would grow differently. A MND universe would predict a distinct pattern. Without the extra gravitational glue of dark matter halos, the web's filaments might be thinner and more fragile. The distribution of galaxy clusters would be less clumpy. The velocities of galaxies streaming along the filaments would follow a different rhythm. In essence, the universe's skeleton would have a different build. This is no longer just a theoretical debate. It is an observational battleground. New astronomical surveys like those from the Vera C, Rubin Observatory and the Euclid Space Telescope are providing data of unprecedented precision. They are not just counting galaxies, they are measuring the exact shapes of millions of them to see how the web's gravity distorts their light, a technique called weak gravitational lensing. They are clocking the speeds of galaxies within filaments with incredible accuracy. They are creating a census of galaxy clusters so complete it will reveal the exact statistical lumpiness of the cosmos. Each of these measurements is a direct test. Does the strength of the web's gravitational lensing match the predictions of general relativity plus dark matter? Do the flows within filaments follow Einstein's script or MND? The early results are fascinating and complex. On the scale of individual galaxies, MND often matches observations remarkably well. But on the colossal scale of the cosmic web, the evidence so far still strongly favors the dark matter model. The web is simply too robust, its filaments too thick, and its clusters too densely packed to be held together by modified gravity alone. The immense halos of dark matter predicted by simulations seem necessary to sculpt the universe we actually observe. Yet the trial is not over. As our maps become ever more detailed, even tiny deviations from Einstein's predictions could point toward a deeper truth, perhaps a new theory that blends insights from both sides. The cosmic web, in all its filamentary grandeur, is more than a structure. It is the ultimate laboratory, a billion-light-year experiment testing the laws that bind reality itself. The fate of our cosmic architecture hinges on a single, unknown variable, the true nature of dark energy. This mysterious force currently drives the accelerating expansion of space, stretching the filaments of the cosmic web ever thinner. But is this its final, constant state, or could it change? The 24th secret confronts us with two starkly different endings for the universe, both written in the future evolution of the web itself. In the first and currently favored scenario, dark energy remains constant, acting as a cosmological constant as Einstein once imagined. If this is true, its repulsive push will continue unabated forever. The consequences for the web are a slow, inexorable unraveling. The gravitational tug of war will be decisively lost. Over trillions of years, the accelerating expansion will stretch the cosmic filaments like taffy. The rivers of cold gas that feed galaxies will be severed. Star formation will cease across the cosmos as every galaxy uses up its last reserves of fuel. The brilliant knots of galaxy clusters will be pulled apart, their gravitational bonds overcome by the stretching of space itself. Each cluster, and eventually each galaxy, will become an isolated island floating in an ever-cooling, ever-darkening void. The cosmic web, the grand design that took billions of years to weave, will be frozen and then dissolved into a featureless, expanding emptiness. This is the heat death, a final state of maximum entropy where no structure remains and no new story can ever begin. But there is another, far more dramatic possibility. What if dark energy is not constant? Some theories suggest it could be a dynamic field, one that might decay over time or even reverse its sign, becoming attractive. If dark energy were to weaken and fade away, the cosmic balance of power would shift dramatically. Gravity, the patient architect, would once again become the dominant force on the largest scales. The expansion of the universe would slow, halt, and then reverse. In this scenario, the cosmic web becomes the blueprint for a catastrophic unbuilding. The great flow that once sent galaxies streaming apart would reverse. Those same filaments and walls, the highways of the cosmos, would become the channels for a cosmic reflux. Galaxies, then galaxy clusters, would begin rushing back toward each other, pulled by the relentless grip of gravity along the web's familiar pathways. The universe would begin to contract. Temperatures would rise as everything is compressed together. The sky would blaze with the light of colliding galaxies as the web collapses in on itself. This would culminate in the Big Crunch, a fiery mirror image of the Big Bang, where all matter and energy are compressed back into a singularity. The web that defined the universe's structure would be the very scaffold of its destruction. Our ability to forecast which of these fates awaits us depends entirely on reading the subtle changes in the cosmic web today. Is the web's growth slowing down or speeding up? By measuring the precise rate at which galaxies are being pulled into clusters along the filaments, and by using the baryon acoustic oscillations as a fixed ruler to gauge expansion over cosmic time, astronomers are taking the universe's temperature. They are looking for any deviation from the constant dark energy model, any hint that the repulsive force is changing strength. Every new, ultra-precise map of millions of galaxies is a snapshot in time, and by comparing these snapshots across different epochs, we can chart the acceleration of the acceleration. The web is not just a structure, it is the universe's most sensitive barometer, its vast filaments trembling with the influence of the force that will decide everything. The story of the cosmos, from its quantum origins to its glittering web of galaxies, is still being written, and its final punctuation marker, a silent, eternal period or a violent, closing parenthesis, is hidden within the dark energy that flows through the empty spaces between the threads. Our own cosmic address might be more humble than we ever imagined. After exploring the grand design of the universe, from its quantum seeds to its ultimate fate, we arrive at a final, deeply personal secret. The 25th secret asks a startling question: are we living in a cosmic void? The evidence suggests we might be. Our Milky Way galaxy, along with our entire local group of galaxies, appears to reside in a vast, underdense region of the cosmic web, a place astronomers call the KBC void or the local hole. This is not a terrifying emptiness like the Boötes void, but a significant bubble of relative nothingness about 2 billion light-years across. We are not at the center of a great wall or a bustling filamentary intersection. We are in the suburbs, a slightly emptier neighborhood on the edge of a cosmic metropolis. This realization carries a profound and unsettling implication. Our view of the entire universe might be biased by our unremarkable address. Think of it like living in a valley surrounded by mountains. If you tried to measure how quickly the world is expanding by only looking at the distant peaks, you might get a distorted answer because your local terrain is lower than the global average. This is exactly what might be happening in cosmology today. One of the biggest tensions in modern science is the Hubble tension, a stubborn disagreement about how fast the universe is expanding. We have two primary ways to measure this expansion rate: the Hubble constant. The first method looks at the nearby universe using pulsating stars called Cepheids and exploding stars called supernova as standard candles to gauge distances and velocities. This gives us a precise local measurement. The second method uses the ancient light of the cosmic microwave background, the fossil from the Big Bang, to infer what the expansion rate should be based on the universe's overall composition and structure. These two methods, one local and one global, should agree, but they do not. They disagree by a small but statistically significant amount. The local measurement suggests a faster expansion rate than the ancient light predicts. Our potential location in the KBC void could be the key to this mystery. If we are sitting in a large underdensity, the local gravitational landscape is weaker. There is less mass pulling on galaxies in our neighborhood. This means that galaxies just outside our void are being tugged more strongly by the dense walls and filaments of the surrounding cosmic web. From our slightly empty vantage point, it looks like those outside galaxies are rushing away from us faster than they actually are in the grand, average scheme of the cosmos. Our local measurement of the Hubble constant could be overestimated because we are measuring expansion from inside a gravitational valley. Meanwhile, the cosmic microwave background measurement gives us a global, average expansion rate for the whole universe unaffected by our specific location. The two numbers disagree because one is skewed by our cosmic address. This idea transforms a technical puzzle into a deeply human story. For all our ambition to see the universe clearly, our perspective is inherently local, shaped by the quiet corner of the web we call home. It is a cosmic lesson in humility. The grand tapestry we have spent this journey unraveling is viewed from a single, slightly frayed thread. Our quest to understand the cosmos must always account for the possibility that we are not at the center of anything, but simply fortunate observers in a vast and intricate design, still learning to see our own place within it. From the humbling possibility of our own cosmic address, we have traveled a path that spans the entirety of reality. This journey through 25 secrets has taken us from the ghostly quantum whispers of the Big Bang to the terrifying voids that will one day swallow the light. We have seen how the cosmic web is far more than a static map. It is a living, breathing narrative. It is the story of how random fluctuations became a blueprint, how dark rivers of matter sculpted the first galaxies, and how magnetic fields and shock waves along invisible threads power the most violent engines in existence. It connects the smallest rules of particle physics to the largest structures imaginable, weaving the past, present, and future into a single, interconnected tapestry. Every point of light you see in the night sky is a story tied to this grand design. The brilliant stars in our own galaxy were forged from gas that once flowed along a specific filament. The faint smudge of the Andromeda Galaxy is our neighbor within the same local sheet of this web, destined to merge with us in a future act of cosmic construction. Even the empty blackness between the stars is part of the story, a testament to the voids and the mysterious dark energy that stretches the fabric of space itself. This invisible architecture is the universe's memory and its destiny, a single story told across 13.8 billion years. So tonight, or any night you can, step outside. Look up at that beautiful lying sky, see the scattered diamonds, the faint Milky Way band, the distant fuzzy galaxies, but now know what lies beneath. Imagine the invisible threads connecting every single point of light, a shimmering, three-dimensional lattice of gravity and dark matter upon which all of creation is strung. You are not just looking at stars, you are looking at the nodes in a network, the glittering intersections in a web of unimaginable scale. You are witnessing the visible signature of the greatest structure in existence. This story belongs to all of us. We would love to hear which part of this cosmic journey resonated with you the most. Did the idea of quantum ripples deciding the fate of galaxies blow your mind? Were you captivated by the ghostly galaxies or the terrifying cosmic voids? Share in the comments which of the 25 secrets changed your perspective, or tell us what other cosmic mysteries you would like to explore next. The universe is full of stories waiting to be told, and the next chapter is yours to choose.